Welcome to this explainer. Today, we are going to demystify the inner workings of single and three-phase induction motors, and we're going to transform those complex, invisible forces into clear, totally understandable math. Honestly, if you've ever looked at a massive piece of industrial machinery and wondered how electrical energy so seamlessly converts into the mechanical motion that powers our entire world, you are in the exact right place. We're going to break down the mechanics, the physics, and the calculations that make the whole shebang happen.
Okay, let's map out our journey for today really quick. We're covering 5 key areas. Number 1, the anatomy of a motor. 2, the rotating magnetic field. 3, understanding supply frequency. 4, calculating motor speed. And finally, number 5, the concept of slip.
All right, part 1, the anatomy of a motor, the physical foundation. To really grasp the magic here, we first need to understand the physical playing field where this game of rotational catch actually happens.
So, we begin with the stator. As the name kind of implies, this is the outer, completely stationary part of the motor. Inside of it, you'll find these vertical poles. But they aren't just solid, boring chunks of metal. They are wrapped incredibly carefully in coiled windings. When we let electrical current flow through those windings, something awesome happens. They transform. They become magnetic poles, instantly creating a powerful magnetic field right there inside the casing.
Next up is the rotor. This is the rotating piece placed perfectly smack in the middle of that stator. Those little circles you might see on diagrams of a rotor, those are cross-sections of the conductors running right through it. The rotor just sits there between our stator's poles, waiting for an invisible force to act upon those conductors and kickstart its motion.
Now, these magnetic poles don't work alone. They work in pairs, specifically a north and a south pole. When they get energized, the magnetic field produces magnetic flux, which always, without fail, flows right from the north pole to the south pole across the gap. It's literally the essential bridge connecting the stationary stator and the movable rotor.
Moving on to part 2, the rotating magnetic field, the invisible catalyst. Now that we've got our physical setup, we need to add electricity to turn these stationary parts into a dynamic, moving system.
Getting the rotor spinning is actually a pretty neat 4-step process. Step 1, the supply voltage creates a rotating magnetic field. If it's a 3-phase motor, this happens totally automatically because the line voltage naturally pulsates with a 120-degree difference. If it's a single-phase motor, you just use a capacitor to generate an extra phase to get that rotation going. Step 2, as this field spins, the rotor's conductors physically cut through those lines of magnetic flux. Step 3, that cutting action generates a current, which then produces a perpendicular torque on the conductors. And finally, step 4, the rotor itself starts to rotate, chasing that spinning magnetic field.
Section 3. Understanding supply frequency, the pulse of power. We know the magnetic field rotates, but what actually decides how fast it goes?
Well, the crucial point here is that this rotating magnetic field doesn't just spin at random. It is strictly governed by the supply frequency of your electricity. Frequency is simply the number of repeating voltage sine wave cycles that happen in one single second, measured in hertz. Now, dealing with constantly changing, wavy voltages in math is a headache, right? So instead, we use an RMS, or root mean square value. It's basically a straight line equivalent representing that effective voltage repeating a set number of times per second. But here's where it gets wild. This frequency isn't the same everywhere. Depending on where you live in the world, the actual physical speed limit of your motor changes based on your regional grid. In North America, the standard is 120 volts RMS at 60 hertz, so 60 cycles per second. But over in Europe and most other countries, the grid supplies 230 volts RMS at 50 hertz. That 10 hertz difference fundamentally changes how fast the magnetic field inside the motor is going to spin.
So how does this grid frequency interact with the motor's anatomy? Basically, if your motor has just one pole pair, the magnetic field completes a full 360-degree rotation in exactly one voltage cycle. But if you pack more poles into the stator, let's say 2 pole pairs, the field completes only half a circle in that exact same cycle. The golden rule you absolutely need to remember is this: doubling the number of pole pairs halves the synchronous speed of your rotating magnetic field.
Part 4. Calculating motor speed, the math of motion. We are finally ready to take these physical components and grid frequencies and calculate the exact synchronous speed.
Think of synchronous speed as a carrot dangling in front of a horse. To figure out how fast that carrot is moving, we have 3 master variables. F stands for the frequency of the supply voltage in hertz. P is the number of pole pairs inside the motor. And NS is our synchronous speed, the speed of that rotating magnetic field, measured in revolutions. Put them all together, And you get this beautifully simple master formula. Frequency equals synchronous speed multiplied by pole pairs. To find the speed of the rotating magnetic field, you just take the frequency, divide it by the number of pole pairs, and then, because we usually want revolutions per minute instead of per second, you just multiply that result by 60. Let's do some quick math. Imagine a motor with one pole pair running on a 50 Hz European grid. Following our formula, we take 50 divided by 1, which is of course 50, then multiply by 60 to convert seconds to minutes. That gives us a blazingly fast synchronous speed of 3,000 revolutions per minute.
But what if we swap that motor out for one with 2 pole pairs, still plugged into that exact same 50 Hz supply? Well, our math tells us we divide 50 by 2, which is 25, multiply by 60, and our synchronous speed is instantly halved, down to 1,500 RPM. The physical construction of the motor dictates the speed limit just as much as the electrical grid does.
And that brings us to part 5, the concept of slip, the catch-22 of motors. We've calculated the speed of the magnetic carrot, but now we have to talk about the physical rotor, the horse chasing it. Here is the fascinating twist to this whole story. Ask yourself, what actually happens if the rotor finally catches up to the rotating magnetic field and spins at the exact same synchronous speed? The surprising answer? If the rotor reaches synchronous speed, it stops cutting the magnetic flux lines entirely. They'd be moving at the exact same pace. This is where the brilliant concept of slip comes in. Slip is the required speed difference between the faster rotating magnetic field and the slightly slower physical rotor. Without this fractional lag, this purposeful, absolutely vital imperfection, no current is generated in the rotor's conductors. Torque immediately drops to 0, and the motor just loses speed until it falls far enough behind to start cutting those flux lines again. The rotor literally has to be a little bit slower for the whole thing to work.
Because it's a dimensionless ratio, we can calculate this fractional slip really easily. You just take the difference between the two speeds, so the synchronous speed minus the actual rotor RPM, and divide that result by the synchronous speed.
Let's plug in some real numbers. If our synchronous speed is 1,500 RPM, but the actual physical rotor under load is only spinning at 1,440 RPM, the difference is 60. We take 60 divided by the 1,500 RPM synchronous speed, and we get a fractional slip of 0.04. That translates to exactly a 4% slip. That 4% difference is the absolute sweet spot driving the machine's power and generating all that torque. It's crazy when you think about it, right? The induction motor, the workhorse of our modern world, relies entirely on the rotor never quite reaching its goal. As we wrap up this explainer, I want to leave you with this provocative thought. If the calculated imperfection of slip is exactly what keeps our massive industrial world spinning, what other invisible, imperfect forces do you think are driving the physical machinery around you every single day? Keep questioning, keep learning, and I really hope this deep dive transformed the way you look at the hidden math powering our lives.